Today, I'm here with Kwanda Zwane, who recently defended his PhD thesis at UCL in the foundational AI CDT. So that was the same one I was on. So welcome, Kwanda, and congratulations.
Thank you very much, Ruben, and thank you also for having me.
So what was the title of your PhD thesis, and roughly what kind of problems were you trying to solve in it?
So my PhD thesis title is Safety-Aware Learning in Real-World Robotics with Gaussian Processes. And the kind of problems that we try to solve is to make it easy to apply machine learning on real-world robotic systems, right? So a lot of the time, machine learning research, especially in robotics, will end up in simulated environments or toy domains, which demonstrate that whatever algorithm or machine learning technique at hand is powerful or has the potential to be useful, but most of the time they start to break down when you approach real world robots.
You train it in simulation, but then when you start doing it with an actual physical robot, it goes wrong.
Yes, exactly. So, and maybe a bad way to summarize it would be that I think machine learning techniques, maybe things like reinforcement learning, would treat robot learning as a sort of unconstrained problem, right? So an unconstrained optimization problem. So you are saying that whatever task I want the robot to do, I will come up with a reward function or some sort of objective function that I will optimize, and I want any policy or decision-making function that will maximize the amount of reward that I get. But in reality, you also need to, in reality, in addition to maximizing the reward, you also need to remember that the physical world is constrained. So there's many forces, there's many unmodeled effects that you find in the real world. There's also friction, there's uncertainty, there's a host of issues that you need to sort of account for, and you need to consider them as best as you can inside the learning process.
I
Yeah.
see. So when you have an RL agent in a simulated environment, typically at the beginning of training, it's just kind of flailing around everywhere. But if you were to do that in the real world, that would go badly wrong. So is it the
Yeah.
training that you want to be constrained and safe, or is it the end policy, the end actions of the robot that you want to be constrained and safe?
Yeah, so it's actually a little bit of both, right? So,
Mm.
or both, actually, not a little bit. You want to be safe during training. You also want to be safe at deployment time, right? So, reinforcement learning is what we do when we maybe don't have a huge data set for a particular problem, or we realize that, okay, we can phrase this problem as some kind of Markov decision process. We can specify a reward function that if the value of this reward function goes up, then hopefully the behavior that we get out of the learning system is close to what we intend for the robot to do,
Mm.
right? So we are mainly randomly exploring, and then we are almost gambling. We don't know what kind of behavior we're going to find, right? And maybe something that is mathematically optimal might not be what you have in mind as the human being, right? And there's a lot of famous case studies where people show that your reinforcement learning agent has the ability to sort of exploit the reward function if you're not careful about how you specify it.
So this is reward hacking.
Yes, exactly.
Okay, so when the human is not perfectly written the reward function, so there's some way to get high reward while not doing what the designer actually wanted the agent to do.
Yeah, 100%.
Okay.
I think maybe a fun example here might be to think about what speedrunners have to do to play any given game
Yeah.
very quickly, right? It involves sort of leveraging the physics engine of the game and using it in a way that's not really intended, right? to achieve some behavior, right? So you end up teleporting around and performing actions that aren't really possible in the real world, right? And whenever the reinforcement learning agent starts to learn behaviors like this, if it's in simulation, it'll be hard to port those behaviors to the real world, right? But ideally, if we put the idea of simulation aside, what everyone really wants who uses reinforcement learning, especially for robotics, is to just run reinforcement learning on the robot. But the problem is that robots are really powerful, they are very expensive, and also the environment and the equipment that the robot will be operating in will consist of yeah, maybe safety critical assets, or maybe things that can break easily. So it is usually better to make sure that whatever action you are getting from your decision making system, you know that this is supposed to be a safe action, whether this is during training or at deployment time. Yeah.
Okay, so the robot could do something, produce some action that's so forceful it destroys itself or ruins one of its joints or hits something in the environment or a person that it wasn't meant to.
Yeah, exactly. Yeah, 100%. So this can happen during training, because in training, classical reinforcement learning will encourage the agent or the policy to take random actions.
Mm,
And if the random action somewhat improves the rewards, the sequence of rewards that you get, then that is going to be sort of reinforced, right? It's going to reinforce this behavior, and it's going to sort of learn something that is more and more similar to whatever this action or sequence of actions that it has found. Now, at deployment time, it's a matter of out of distribution generalization, right? So it's more like
mm,
this reinforcement learning agent is now being given data, or the policy that you got is being given data, and it has to sort of make instantaneous decisions, right, at some very fast frequency. Now, if for some reason the environment changes, maybe it was learning how to pick and place a cube on the table or doing something useful, and someone comes and replaces the cloth on the table, which used to be red, with the blue cloth. And now all the images that the agent is seeing are very different. And then according to the model, maybe this is no longer a table, maybe this is something else. And the actions that come out of the robot in that setting should also be safe, right? So
mm.
you need to minimize surprise, if I can put it this way.
I
Yeah.
see. Okay, so there's one step of like, you don't want it to do anything crazy during training and break anything. And then also the final
Mhm.
policy, you want that to be like constrained and safe. And also
Yeah.
like in new environments that it's not seen before, you still want it to be constrained and safe.
Yes. Yes.
So let's go into the solutions a little bit. How do you actually get these constraints into an RL agent?
Yeah, so the first thing is maybe thinking about what we mean by constraints, right? So constraints can be in the most I think in robotics people will like to think about obstacles in the environment, right? So you are trying to manipulate a particular object, but there's other objects around it, or there's the table, or the walls and things like this. So now, for the reinforcement learning agent to be aware of these things, or for the robot or whatever learning system you have in place to be aware of all of these constraints, you need to somehow encode them mathematically.
Mhm,
And people will use, kind of fancy perception systems. They will use some kind of sign distance field, right? So the unfortunate thing is that most of the time you need a lot of information ahead of time about the environment that you're going to be deploying the robot in,
mhm,
to know how to in order to model that environment um, enough to embed it into whatever learning framework that you have, right? The main thing is that we need to be able to model the environment and the obstacles and all of these constraints, and at some level you are no longer performing optimization with a single objective function, but you can imagine that you are sort of doing, I want to optimize this objective function, whether it's a known function or not, subject to these sort of constraints, right?
mhm,
And then you are optimizing a certain set of parameters. And if your model is interpretable, then maybe you know what those parameters stand for, and you can somehow make some conclusions around if the parameters have this value, this is the behavior that I can get out, or this is the behavior that I can expect, right? So unfortunately, with kind of complicated models, such as neural networks, it is a difficult task to sort of understand how the model is going to behave, right? You don't know what any um, configuration of these weight matrices um, is going to result in behavior-wise. But certain models, like Gaussian processes, are extremely interpretable, and that's maybe the reason why I decided to go with this model and kind of like see how far we can stretch them in robotics applications. Yeah.
So, like, let's take a really simple example. Like, suppose you got a robot and there's a cup on the table, and you want it to do some task on the table while not knocking over the cup. Um,
Mhm.
could you just have like some other program that's running on top of the RL agent that where the RL agent produces like an action sequence, and then this other program just checks, is that going to hit the cup? If it's going to hit the cup, reject and sample a new action sequence. If it's not going to hit the cup, just carry on. Like, is that the kind of thing you're doing, or have I completely misunderstood that?
Yes, exactly. So actually, I do have a paper which uses a very similar approach of like a rejection sampling. So,
Oh,
um,
okay.
I suppose that there's a few ways to think about where to put in the safety, right? So if you, the human, engineer what safe and not safe is, and your environment is simple enough that you know that there's a clear boundary between safe states and unsafe states,
Hmm.
right? Then you probably are better off engineering that safety layer, like some kind of program or watchdog that's going to evaluate whatever um, sequence of actions comes out of the RL agent, and then maybe even before applying them to the environment, you already add a term or some kind of penalty term to the reward function based on how safe these actions are. But for the same reason that the model that produces the actions, the policy, for the same reason that we choose to learn this instead of actually hard code it or make it a program with a lot of if statements, these sort of safety layers can also become very, very complicated in certain domains. Right.
Hmm.
So in the example that you gave, where you have some process that evaluates the sequence of actions that come from a policy, and then you say, okay, I'm going to reject this, I'm going to accept that. Um, what if the inputs the inputs that this process has to look at include deciding whether a cup is full of water or not. So if the water is kind of like filled to the brim, and then it's not overflowing, if you get what I mean.
Uh-huh.
All right. So if you have a model that's supposed to decide, is it should the robot stop pouring or should it continue pouring water? That is very complicated, and you need actually a learned model, because it's really hard to represent mathematically whether some liquid is like overflowing or not,
Right.
especially in different lighting conditions. Right. So that can be a kind of like safety function. It can be an entire model with its own set of inputs and outputs, and all it does is just it's an objective function or kind of queue network, which instead of looking at how well we're performing at the task, it's looking at how well we are doing at obeying the constraints. Yeah.
Okay, so a very simple like constraint, like don't hit the wall. You could have this kind of
Hmm.
process that's just a gatekeeper. That's like, oh no, you're about to hit the wall. You're not allowed to do that. But
Yeah.
if the kind of safety behavior you're trying to embed into the system is much more complicated, like with a self-driving car or like pouring water, like you said, then you need a whole network
Exactly.
to learn what's safe and what's not.
Yeah. Yeah.
Okay,
Hundred
okay.
percent. Yeah.
And then this network presumably gets things wrong occasionally. Like it sounds like this is just a very hard problem to solve.
Yeah, so and the network, as people say, will be as good as the data that it has seen, right? And
Hmm.
then that data will be as good as however similar the deployment conditions are to the data collection conditions, right?
Hmm.
So for many reasons, even if you're a self-driving car, roads will change over time, right? Maybe there's potholes, there's new effects and
Mm,
stuff. Um, Sometimes the sensors that you use start to change, and then that changes your like the data that you see as well, which can also degrade performance.
mhm.
Yeah, but these are many effects that can work against you if you're trying to deploy any data-driven system in the real world, right? And for some applications, just to add, for some applications, you can't get away with, oh, it works 80% of the time or 90% of the time, right?
Yeah.
If you wanted to do something like surgery, you need the system to have very low failure rates, like
Yeah.
extremely low failure rates. Yeah. And in those cases, you need to know why it fails. Yeah.
Right. So it can't be like, oh, the operating table was red rather than blue, and so it stabbed the surgeon in the heart just randomly.
Yeah, I mean that's useful, right? So if you can tell people beforehand, be like, never put a blue tablecloth, and then people know, okay, if we put a tablecloth and we were told not to, then maybe it's our fault. But if you don't know what to tell them and be like, it might fail based on something that I don't know, that is
Mm-hmm.
not useful at all. That model, despite its high success rate, might be as useless as one that just doesn't work at all.
Mm-hmm.
Yeah.
So is this the
Mhm.
technique you used of having a separate network to judge whether an action sequence is safe or not?
So in my case, it wasn't exactly a network watchdog process. Um, in my case, I basically had the boring programmatic solution, which checks if we have violated constraint or not,
The
right?
gatekeeper.
Um, a gatekeeper, so to speak. So it's more like there is different within reinforcement learning for this particular project. We have model-free reinforcement learning, which is just um, you want to learn the policy directly. The thing that you're interested in is you want the function that gives you the actions. It takes in the state, gives you the actions, and the way that you make this function better is by trying it on the actual environment or in a simulator where you can get data for free.
Mhm.
But you can also do something called model-based reinforcement learning, where you first uh, build a model of the system, which is if the system is a robot, then you have some function that will say, well, in this state, if I take this action, this should be the next state. So you learn a sort of transition function.
Mhm.
And now, once the transition function gets good, you can start getting data from the transition function instead of asking for data from the real system, right? So this is useful because you don't have to evaluate an entire action sequence on the physical robot. You can just throw that action sequence at the dynamics model, which you have learned, and that should sort of give you an idea of how this will behave on the real system. And doing model-based reinforcement learning is data efficient because you end up needing less data, magnitudes less data normally than what you would need for the model-free case. So in the project that we were working on, we were thinking about, in addition to making this dynamics model really good at simulating what will happen if a certain sequence of actions is applied on the system, um, could we also make it give us a sequence of trajectories, because it produces trajectories that are safe, right? So I think normally when people do model-based reinforcement learning, there's not a lot of emphasis on the quality of the simulations or the quality of the data you get out of the dynamics model. It's just taken as is and then used to update the policy.
Mhm.
So we had an extra step where we had to check, is this action sequence or is this trajectory that we got from the dynamics model safe? Is every state in this sequence obeying our constraints? And is it smooth? Is it something that the robot would be able to execute if we had, is this a realistic trajectory that we would have gotten from the robot had we not used the dynamics model? And then if the answer is no, if there's any constraint violations, if it for some reason is not continuous, then we just reject it. And then if it is good, then we we will put it in some kind of, I don't know, buffer, or we will put it in a database, and that's the data that we use to update the policy. And we found that even without telling the policy about the constraints that it needs to obey in the real world, just by giving it access to this sort of safe dynamics model, you can somewhat bias it to take safer actions without the policy being entirely aware of the constraints that it has to deal with in the real world. Yeah.
So you're not exactly punishing it for doing something unsafe. You're just saying you don't get to use that data to improve your world model.
Yes.
Huh.
Yes. Because it's more like well, it doesn't make sense to train the policy on data that's never going to happen in the real world,
Right.
and it might even be a bad idea to do that because now it might give you some unexpected behavior whenever it goes out of distribution, right?
Yeah. Yeah.
But if we step back from what the policy is, it is basically a machine learning model of some kind, which is trained to sort of mimic whatever data distribution that it's been trained on. So the idea being that if you give it a safe sort of data distribution, it should learn to produce actions that keep it inside that
Right.
safe data distribution, right?
I
Yeah.
see.
Or,
I
or,
see.
or in reinforcement learning, we refer to regions of state space. So you want to stay in the regions of the state space which are safe. Yeah.
Okay. Let me have a
Mhm.
go, see if I can understand. Repeat this back to you. So, like, you've
No
got
problem.
model free reinforcement learning, which is where you just try
Hmm.
and learn the policy directly, and
Yeah.
it's very hard to tell like whether that's going to produce safe results in new environments or to like
Hmm.
constrain it during training. And then there's model-based reinforcement learning, where the agent is not just learning like what are good action sequences, but also how does the world work? Like what actions in which states lead to which next states. And then you can sort of
Yeah.
keep an eye on the model that the agent is building up. And like one, check like whether it's accurately reflects the real world, and two, like check whether it's about to experiment doing something that you would consider unsafe. And
Hmm.
if it's going to do an unsafe thing, you just like stop it there and say, no, you're not training your world model on that data. Let's sample again. And then you end up
Hmm.
with an agent that like knows how the world works, but only the safe bits of the world. And then so only acts in a safe way that like keeps it in these safe states in the in the world model it has. Is that roughly correct?
Hmm. Yeah. So maybe a few adjustments there. So with regards to the model free reinforcement learning agent, so all we're doing there is we are definitely learning the policy directly, and maybe the main thing to highlight is that the policy isn't necessarily learning a world model of some kind, right? So we could say it is doing that implicitly,
Hmm.
but it is simply a model that takes in the current state and says at this state the right action is this one, right? It's just the function that we use to make decisions.
Hmm.
And then in on the model based side, you sort of split learning into two. So you have to learn a dynamics model, and the dynamics model is basically your world model, or um your understanding of the world, right?
Hmm.
So meaning that these are the dynamics. If I observe a ball, I apply a force to it, this is where the ball will be based on what the force was. So that's the kind of model that we're thinking about.
Hmm.
And then the policy is still the same policy that we had when we were in the model free setting. But now the model can be used, the dynamics model can be used to sort of imagine what the consequences of any given sequence of actions is in the real world without having to actually apply it. Right.
Hmm.
So as a human being, you know that if you're cooking and you switch on the stove, you should not touch the stove. If you do touch the stove, you're going to burn. That is something that you understand very well. You don't need to actually burn to know that the stove will burn you, right? Yeah, so it's a sort of like a similar idea. I think that's a classical motivation for the model. And in recent times, people don't think about one-step dynamics models. They think about world models, which maybe take a single start state and a sequence of actions to apply from the start state, and then the world model will kind of show you what happens if you apply that sequence of states from this particular, you know, um, from this particular starting state. Yeah.
Mhm. Okay. And then when you tried this method out, did it work? Did it produce a safe robot?
Yeah. So I want to say it kind of works, which is surprising because it seems like a silly thing to do. I'm only going to train the policy on safely simulated trajectories. So trajectories
Hmm.
that come from a dynamics model that are safe or that obey the safety constraints, right? So it would work. But sometimes you run into issues such as, because we're doing rejection sampling, which is not really a it's not the best form of sampling that you could do, but you are doing rejection sampling, and that means that you end up with a smaller training set for your policy. And maybe there's even though the other trajectories that we threw away were unsafe, they might have had a utility for helping the policy explore.
Mm.
Right. Maybe it was optimal in some strange setting to take a bad action or an unsafe action that's never going to be possible in the real world. But in return you discover the right action, right? So those are sort of, I think, still open questions. But the issues with the method that I'm discussing is that perhaps you need a more intelligent form of sampling that doesn't completely get rid of the bad samples, right? Even now, when people sort of train robots in a supervised learning way, um, people have found that it's useful to add a few recovery demonstrations, right?
Mm.
So in imitation learning, where you're demonstrating a particular task, you're teaching the robot to fold a towel, to stack some cubes. Um, Maybe a wise thing to do in that context is to add demonstrations for how to recover from when any given demonstration has been done incorrectly, or if the agent ends up in a bad state, how to come back from that into the nice set of states.
I see. So if it's never seen things going wrong, then it will have difficulty recovering when things inevitably do go wrong.
Yes, yes.
Okay.
That's basically the intuition there. Yeah.
Okay. Interesting. So you sent me this paper you worked on during your PhD where you were first author. So it's learning dynamic tasks on a large-scale soft robot in a handful of trials. And I assume this picture here is, well, there's the simulated robot, and then you have the real
Mhm,
robot here. So can you tell
mhm.
us about this paper?
Yeah, so in line with the theme of trying to learn safely and learn in a way that is still compatible with the physical real world system. In this paper, we took a different direction. So instead of looking at um, safety and constraints and modeling them directly, we looked at a set of, maybe a system, a robotic system that is inherently safe. So this is a soft robot, and soft robots are kind of bendy. They're known for being, yeah, soft, and in some cases they can take. In a lot of cases, they can basically take more impact compared to rigid robots, which is what people imagine when you describe a robotic system. In return to having this extreme flexibility, you end up with all the complexity on modeling the robotic system, right? So if you're a rigid robot, it's basically a bunch of sticks with angles, and like there's some convenient geometry for computing where the end effector or the hand is going to end up in 3D space based on all the angles of the arm. But you don't have such convenient mathematics for systems like this. And then estimating the state of the robot so that you can make a decision is extremely difficult, and modeling the robot is yeah, quite challenging. So
Mm.
what we did in this paper, we said, okay, we accept that modeling a soft robot is challenging, and we're not going to do that. We're not going to model the system. Instead, we are going to try and learn the policy directly. Previously, I think people are used to first coming up with some physics model, some first principles based model of a soft robot. And then once it's sort of accurate enough, then you can use it to define some kind of controller that can make some tracking tasks and things like this. But this is a huge effort, and these models are typically not portable between soft robot platforms, right? Does that make sense?
What do you mean by portable?
So by portable, it's more like um, soft robots are not quite standardized, right? So if you're thinking about this robot that is a large scale one, it's
Hmm.
about 1.2 meters in length versus a very small one that is used for surgical applications. They all are sort of like snake-like robots, but they are not really similar. Like there's not a lot of standardization in the design.
Hmm.
So if you're going to derive some kind of physics-based model for one of these soft robots, you probably have to do the whole process from scratch when you move
Right.
on to a different robot.
Right.
Yeah.
So a hard robot where it's just like sticks with angles. Like it doesn't really matter
Yeah.
how big it is, whether it's tiny or massive, it still just sticks with angles, and that's how it's going to move.
Basically.
But
Yeah.
with a big soft
Yeah.
robot,
Yeah.
like the way in which it flops around is going to be very different if it's like a tiny one where it might be like more stiff, or a massive one where
Mhm.
it might fall more under its own weight, that kind of thing.
100%. And then also it depends on what it's made of. So some of them will be made with plastic, some of them will be made with, I don't know, like some kind of steel rings
Mm.
and things like this. Some of them will be pneumatically driven and they'll still work like an elephant's trunk. And some of them will be cable driven, which is, there's some motors that spin and then pull different sections around to actuate the robot. And all of these will sort of have different dynamics, right?
Hmm.
And hence kind of coming up with some standardized model that's going to work for all of them is extremely challenging.
Mm.
So in this paper we decided to just throw out of the window all of this modeling literature and said, well, what if we could look at learning um, a controller directly or the policy directly, right? Because at the end of the day, we want to perform a task, which is maybe we want to do a throwing task or we want to do a hammering task. And you can sort of describe this as a Bayesian optimization problem, which is how we're able to solve this task in a handful of trials. Bayesian optimization is extremely data efficient. So what we do specifically is that we say, okay, we're going to come up with a convenient parameterization, um, some um, set of parameters, which if we choose values for those parameters, they give us a sequence of actions for our robot. Right. Now it's a matter of finding the right values for all those parameters such that we optimize the utility function or objective function. Right.
So the parameters that you have for the model, I mean, this I think in the paper you said the arm moves by having little pistons, like air pressure pistons, and so the parameters are like how high is the air pressure in this piston at
Hmm.
that time instant, and then you said that like
Hmm.
if you list all of those, you actually have too many parameters because you have like 5 time steps or something and 12 pistons, so you have 60 parameters. Um, for each of the piston pressures at every time interval. And 60 is like too high dimensions for Gaussian processes. And then you do some clever trick
Hmm.
to reduce the dimensionality to below 20, which I think you said is
Yeah.
like the recommended maximum for a Gaussian process. So what do you do once you've got
Yeah.
these parameters?
So if you've gone through the trouble of defining maybe a small set of parameters whose values which you're trying to optimize over, right? And there's some kind of objective function which is unknown, right? And you're going to be modeling that objective function using a Gaussian process, right? So firstly, what you'll do, maybe you'll start with a few random parameters, and then you're going to evaluate them, and that gives you data, right? So evaluating it is that, okay, I tried 0. 0.1, 0. 0.2, blah, 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 blah. And then I got a sequence of actions that I applied, and then I got an objective function of this value. And then that gives you a data point, right? And then you try a different set of parameters, and then you get another data point. Now you're going to fit a Gaussian process over these data points, and then you're going to get some kind of like trend. So the power of Bayesian optimization is that it can explore efficiently um, in this within this surrogate model, right? So you are maybe sometimes depending on the acquisition function, you might want to look at areas where you have the most uncertainty, meaning I mean areas where you have the least amount of data, right? Or areas that are the biggest gaps. So you start there,
Mhm.
right? And by checking iteratively like this, you might be able to find the parameter values that give you the best policy quickly. Right. So using this technique, we were able to find a policy for throwing a cube, which I think we threw about maybe 4 meters or so in simulation. And then in the real world, we didn't do a throwing experiment because just the mechanics of throwing with a soft robot. If you don't have a robot arm which can grab something, the next best thing you can do is you have a steel ball and an electromagnet and you release that at the right time.
Mhm.
But no one is super thrilled about throwing a steel ball indoors with like a big robot. So maybe it's better to just measure. Yeah, it's better to just measure how fast the end effector can go.
Uh-huh. As a proxy for how far the ball would go if it was actually throwing the ball.
Yeah, 100%. And then the other task is hammering, right? So hammering is a task that is unique to soft robots in the sense that it's difficult to hammer with a rigid robot because it's hard to absorb the impact with like a rigid structure, right? So if you
Mm.
hammer it, it's going to go straight to the actuators and damage them.
Mm.
But if you've got like a floppy robot, like it can take all the impact without actually losing structure or stuff like this. And even with throwing, you need like some kind of flicking, right, to actually throw properly. And it's hard to do this with rigid robots, right? Or it might be algorithmically hard, but the big soft robot that we consider here potentially has the ability to throw further than a human being can because of the way that it can flip. Like it's basically can potentially flick whatever it's throwing in the same way that you would flick a whip, you know.
I see. I
Yeah.
see. You build up some momentum and then flick it all to the end of the robot. Um,
Yes, yes. And that's difficult to hand engineer, right? Which is why we're sort of like learning this in the first place. And we hope we have the right objective function
mm.
because reward misspecification can still happen even in this context.
Yeah,
Yeah.
yeah. So you have this robot that's soft and like can get damaged. So you want to be able to learn
Mhm.
very efficiently in a very small number of trials. And you said you managed to train this in a handful of trials. Should I take that literally as like a few tens of trials or?
Yeah, yeah, exactly. I think we got we got good behavior in around 60 trials.
I'd call that a handful, yeah. In reinforcement learning, that's incredible.
Yeah, yeah. And then I think the reinforcement learning agent needed like way more data after an initial pre-training phase to actually converge to something that makes a little bit of sense. And even in that case, after convergence, in some instances it could not beat what we were able to find using Bayesian optimization. We had to sort of model the robot in a simulator as well,
Mhm.
and the way that we model it is sort of like a little bit different from how the actual robot operates, right? So the robot has got a bunch of plastic chambers where you pump in air on this side, and then you create a vacuum on this side, and it bends this way, and
Mm.
then you've got those sort of sections stacked on top of each other, like three of them. But in the simulator, we just have a bunch of disks with some forces, and they are sort of like a big chain of disks, and you actuate them that way. Um, but we didn't need to change the algorithm that we were using. Like Bayesian optimization was easily portable without any changes from the simulated environment into the real robot. And if someone is working with a I don't know, maybe a similar robotic system, there's not a lot of hand engineering that needs to go into place. They just need to present a set of parameters that would help actuate their unique robot platform, and then the algorithm would just work. Yeah.
That's pretty cool. So in 2024, you did an internship in Japan in Tokyo. Can you tell us where you were
Mm.
and what you got up to there?
Oh yeah. So the internship in Tokyo was in a research lab, which is in a research institution in Tokyo called ICE. And this particular research lab was looking into how robots integrate in society, right? So it's more like AI for human spaces, and they had a cool project. My supervisor, Dr. Yoko Sasaki, there was working with a science museum next door, which was the one building over, and they would once a month maybe go and showcase their robots. So she had a bunch of mobile robots, which would have to autonomously navigate through the crowd. So now the sort of research problems there is how do you as a robot move through a crowd of people if it's like a very busy place like a shopping mall in Japan or a museum. How do you efficiently take the shortest path but also abide by social etiquette, right? So there's no abrupt stopping, abrupt like movements and stuff like this. You can't exactly cut through people in some cultures. So you have to do it in a way that is socially sensitive. And you need to model every group of people that comes towards you. And also it may help to model, I don't know, the age group as well. So if someone is below the age of 5, the chances are their velocity is very high and they're just running around all over the place. And there's a big chance that they're going to run up to the robot and try to shake it or do something like this.
Alright.
So things like that and thinking about how to handle that is very, very interesting. And then the lab that I was in also had a fake kitchen. Um, so it had like a kitchen environment where you could maybe drive robots into and then maybe teach the robot how to I don't know, wash the dishes and do all these sort of tasks. They had projects on swarm robotics, which is many small mobile robots, and how they might be used to sort of build a map of a very large area, or how they might share information,
Right.
and stuff like this. So the project that I was working on is trying to see if we can use Gaussian processes in some way to model the way that people move around the robot, right? So, because the robot is not a human being, we don't have to constrain it to the same embodiment as a human being, which is, if you think about it, a little bit limiting because your eyes are in your head. But if you're a robot, you can have eyes in the environment. You can put like cameras everywhere, all throughout the corridor. And
Yeah.
by the time a person gets here, you know maybe how tall they are, how fast they are moving, and things like this. And you've already modeled their future trajectory. And that is important because if you know that they intend to go in that particular direction, it means that you can go that other way.
Hmm.
Does
Hmm.
that make sense?
Yeah, yeah.
Yeah.
I imagine having eyes that are only in your body. How limiting.
Yeah, I mean, yeah, exactly. I mean, maybe not so much, but yeah, I mean, it would be nice to be able to see in that other room, right?
So
Yeah.
did you manage to get the robots to be polite and step out the way or walk around people?
Yeah, so I think this, based on the time, like we were only able to sort of make some nice plots. I think of just like, oh, this is um, um, a vector field of how people will move,
Mm.
modeled with the Gaussian process in some 2D spatial way. But yeah, we did not get a chance to actually apply that on the actual robots while I was there. But I did get to actually babysit the robots while they're at the museum. So while we are deploying some of the algorithms that other people in the lab worked on, you will sort of watch the robot do whatever it's doing back and forth, just navigating there, avoiding people, and everything is working. But there'll be like at least one case where the robot gets stuck over a slightly elevated piece of the floor. And then you need to either go and control it with the joystick or just actually move it. Other times it's being careful that it doesn't hurt people because children will really come and shake the robot and play with it and things like this. So if the robot moves forward a bit or goes back or gets confused about what to do and someone gets hurt, then that can be a big problem. So having human intervention is really useful in that case. So I was, I suppose, standing around and making sure that everything goes okay.
Are the robots child-sized or smaller?
Maybe as tall as a 5-year old, maybe
Okay.
as like a meter or so.
Maybe you need to make the robots bigger and with a scary face.
Yeah, I don't, I don't know about that. Yeah, there are robots that are that size, but interestingly, another project we had was autonomous wheelchairs. So you get these wheelchairs that have got a lidar on them, and they can model the environment. And then the idea is there is that people who are immobile, and maybe can't actuate the wheelchair themselves, or just for convenience, can just sit and tell the wheelchair, okay, I don't want to go there in the map, and the wheelchair can just
Mm,
autonomously navigate in a way that is also socially acceptable.
mm.
Yeah.
Yeah, that would be
Mhm.
really cool. Are we anywhere near that kind of application coming to
I
fruition?
think very close. I think very close. It's probably, to me it feels like a solved problem for known environments. So if you know the environment beforehand and you've kind of gone to the trouble of building a map and there's not going to be any new obstacles and it's just people and you've got your cameras all over the floor and you've got a nice powerful computer in your wheelchair, that to me feels possible. Yeah, like
Cool.
very reliable. Yeah,
Like in a few years, you could feasibly have that.
I think some people might already have it, but yes, I
Oh,
think in a
okay.
few years definitely. With sort of these kind of research problems or research directions, whether they make it into the real world is sometimes, after you know that the technology is feasible, there's also additional considerations that have to do with commercial feasibility and
Yeah.
like, is there a
Mm.
demand for it? Is it actually useful? Is it taking away jobs? Do we actually need this service? This kind of thing.
Yeah.
So if all of those boxes are checked, I think you should be able to see that at least in like airports and old age care homes, perhaps.
Hmm.
Not sure.
That's
Yeah.
cool. That's cool. So while you were doing your PhD at UCL, you also co-founded the startup Amatambo AI. Can you tell us what inspired you to do that and what problem you were trying to solve?
Yeah, so my friends and I, who are my fellow co-founders of Amatambo AI, we're all international students. We're all sort of African students in different places around the world, and there has always been this need to give back or apply the skills that we learn in whatever sort of well-resourced institutions that we find ourselves in, back in our home countries, or try to solve some kind of like socially significant problem. And
Hmm.
so all of us are sort of well versed with machine learning, and Amatambo AI was born out of this kind of ideathon competition around COVID, right? So the challenge was that we needed to come up with some machine learning solution that would help solve some social challenge. And the one we went with was, oh, we're gonna, come together and try to predict bed capacity at different hospitals. So we're going to use machine learning tools and try to, maybe get a bunch of data and sort of let hospital management know, um, I don't know, the usage of different hospital beds, and maybe they can use that to make decisions around where to route their resources. And then later along the line, Amatambo kind of took shape as sort of a startup that is trying to address resource constrained healthcare systems all around the world at this point. If we look at the problem this way, right? So if you are a hospital and you're working with a limited set of resources, we can solve this problem by either throwing money at the problem, maybe through some charities and philanthropists and things like this. But we can also try to somewhat solve the problem by helping these hospitals make best use or better use of whatever resources they do have. So we thought that, we can use some, kind of like off the shelf mathematical algorithms and some fancy optimization to help people use, firstly, allocate their staff better. So give doctors better working hours, try to reduce waiting times for patients who have to wait long hospital queues in many third world countries. And then the last part is trying to help hospitals or healthcare centers manage the usage of medical equipment, right, which is also limited. Some countries have very few MRI machines, for example, and also medical products. So a lot of medicine, maybe around winter, is going to be required, and there's seasonality in the usage trends that you can learn using machine learning, and then you can make predictions around how much to order. And maybe there's other features, predictive features that you can absorb from the catchment area of the hospital that can inform how you can run the hospital. So our first product is called Manje, and Manje is a rostering application. And this is an application that helps you with timetables for what hours your staff are going to be working, right? Which is supposed to be simple if it's a normal 9 to 5 job, but hospitals have to work with these strange post-call environments where one doctor has to stay after the regular 9 to 5, maybe until the next day. And then after they've worked for that long, they can't, work that entire day because they're exhausted. So if you're trying to schedule this kind of timetable with your head, it's really difficult. It's actually an NP hard problem.
Yeah, humans are not famous for solving NP hard problems in the head.
Yeah, exactly. Another thing is a little bit inconvenient with and being human, I suppose. But yeah, the way that we try to solve this is we we use, I suppose, just optimization, like it's mathematics, um, and we put together a tool that can produce this optimal roster that balances when your doctors are going to work, when they would like to have leave, and then also potentially later, like features we want to add include sort of using some kind of predictive model that tells you how much capacity to expect at the hospital on a given day, and then you can forecast how busy it's going to be for the next 3 months, and then you can create rosters that sort of reflect those predictions, right? Of course, at the end of the day, a human can look at this and be like, oh, okay, maybe we need to change this a little bit there and there, but the rosters that we produce efficient, fair. They come up. We can produce them in 3 minutes, whereas it might take a professional senior doctor something like 2 weeks, right? And the other
Right.
thing is that no one is playing the blame game, right? So it's not a matter of one doctor who might be biased towards um, certain people that he or she likes, because we're all human being and we all always have favorites and things like this. This can be, computationally fair. Like everyone is working the same amount of hours, and things that cannot be quantified easily, like how many weekends someone is getting, how many holidays someone is getting. You can throw all of those into the optimizer, and it has no trouble spitting out a few different rosters, not just one, in a few minutes, right? So we're at a stage where we are trying to we're trialing this tool that we came up with to see if it's useful for some big hospitals in South Africa. We don't have any, I would say, people who are using it on the day to day, but we're treating it as sort of like an experimental project to see, okay, cool, is this a useful tool? Will this help at all? And then if it doesn't, then we
Yeah.
have to sort of like reprioritize and think about what exactly is the problem.
And so now you finished your PhD, you're working at Kinesi. So this is a robot company. What kind of things are you doing there, and what kind of robots do you work with?
At Kinesi, so I'm working on humanoid robots. So for most of my PhD, I've been focused on manipulation problems. So, just a single robot arm with a few, you know, um, I don't know, objects. You either manipulating something, you are doing some reaching tasks. But now you have a full robot that can move around on its own. It's, got
Mm.
wheeled base, and then you've got two arms, and it's a really, really useful platform. It's got interchangeable sort of like grippers and arms. So you could, depending on the context, it might be useful to have prismatic grippers. It might be useful to have finger grippers.
What kind of applications are they looking at? Like stacking shelves, or what are they doing with these robots?
Yeah, so I think the applications we're looking at the moment have to do a lot with warehouse environments. So just being able to man warehouses, move kind of like tote baskets around, like ship
Mhm.
packets, take them, scan them, place stickers on them. So things that would happen in a warehouse, maybe where you ship packages or like you pack, I don't know, food items, this kind of stuff. So they are very strong, I could say. Like it's very surprising how strong they are in terms of like how much they can lift. And features that come later have to do with trying to get them to, I don't know, swap their own batteries, this kind of thing. Um, they like the main idea, I think, is that you're producing these autonomous robots and you want a fleet of them to kind of like man a warehouse. And then maybe in an ideal future, it's just, all robots and no human. And
Mhm.
maybe you if the end application has to do with you ordering packages, then there's a robot that goes to a specific shelf, gets it, and then whatever shape or form the package is, puts it wherever it needs to go, goes on a conveyor belt. Another one picks it up, scans it, and takes it to where it is supposed to go. But yeah, they
Mhm.
are supposed to be extremely versatile robot units, I can say. Yeah.
Wait, they can change their own batteries?
I want to say not yet, but this is something that we are
Okay.
actively, yeah.
Well, when they take the battery out, then they're dead. How do they have two batteries and they take them out one at a time?
Yeah, you could just use two batteries and take one like
Okay.
take one out at a time, right? Yeah.
That's kind of weird to think of a robot changing its own battery. So that creeps me out.
Maybe let's talk about high autonomy and low level autonomy, right? So if you are a robot vacuum, you don't need to be super intelligent, right? Like you can be as dumb as you like. The world is just flat, and you can bump into anything because you don't have a lot of force. You're not going to break anything, and you're just vacuuming things. And things like cables on the floor, you can overcome those challenges by just cleverly designing the wheels, right? And that is
Mhm.
done. And then, like full autonomy is maybe having a robot unit in your home, right? Um, which can cook your meals, it can feed you, it can make your bed, it can do all these things. And if we're going to make a bet on machine learning being the way forward, or like these vision language action models and foundation models and world models being the way forward, then it's a question of how much data can you get and whether you have the right data for your specific robot embodiment, whether you have trained in a setting that is very similar to whatever deployment situation you find yourself in, right? And that's going to require a lot of perhaps standardization, but people have different kitchens and this stuff like this. And I'm not saying that kind of robot is impossible, but that takes way more effort and maybe is a few years out in terms of being extremely useful and extremely practical. A few years out or more, in my opinion. But if you think about warehouse environments, there's already a lot of standardization. There's a lot of how can I say, rules around where the robot needs to be. People can avoid the robot. They know you can sort of control the environment to a large degree,
Yeah.
and the autonomy that you need is not the same as what you would require if you were working in like some random person's house, for example, right?
Yeah.
So it's somewhere, I think, in a nice sweet spot where we believe, I think, that this is possible now, right? If you can control the environment, if the robot is going to be doing, kind of like a set of tasks, you need to teach it new tasks in the same environment. It's not that big of a jump versus having a robot that's going to know how to make you a cup of tea, and then I don't know, you have if you have a child at home and they go to school and they come back with their art project, which happens to be a mug of some kind, but it's a badly misshapen cup, and they want the robot to make them a cup of tea with this weird looking mug. Will the robot handle that? This kind of thing, right? And
Yeah.
yeah, in my view, maybe we're not there yet, but there's certain things that are already possible with the current advancements. And then if you blink and wait 6 months, the field has already like accelerated so much.
So
Mhm,
zooming out for the last question, a lot
mhm,
of roboticists I talk to are really excited about robots and what they'll be able to do next, etc. But then I think a lot of people's first exposure to robotics is something like Boston Dynamics, the YouTube channel, where
Yeah.
they've got this dog or this humanoid robot doing backflips and throwing bags of tools in the air or whatever. Um, and if you look at the comments on there, it's like 90% is people saying like, "Oh God, we're going to have robot soldiers soon." Uh,
Mhm.
like I agree. Like you said, we're not yet there yet. The environments are too varied in order to get
Yeah,
robots
too
to really
varied.
work properly.
Yeah.
But like we're gonna get there eventually.
Mhm.
And we've already got drones entering warfare. Like, what's the kind of vibe in the robotics community about this kind of thing? How do people think about it?
Yeah, so I can only speak about myself. Like, so personally, I like to avoid anything that has to do with my own values don't align with
Hmm.
yeah, producing tools that can cause harm to another human being. I would say I work on robots mainly because they are cool. Like, I think it's cool to watch code do a backflip, right?
Yeah.
I think it's cool to enhance the quality of life using really cool technology. Yeah, as far as warfare is concerned, this is the harsh reality. I think like some people will say there's always two sides to some innovation, right? Whether we're talking about robotics, whether we're talking about generative AI models, which can be used for entertainment, kind of creation and ideation, but they can also be used for misinformation and kind of like spreading fake news, this kind of
Hmm.
thing. So, I think a lot of tools that people develop can always be misused, and yeah, maybe in my view, the army is not the army, but military applications for robotics is one of those, right?
Yeah.
Yeah.
Do you think it will
I
happen
think,
eventually, though?
yeah, I feel like I don't have the right PhD to answer that question. I feel like it's already happening,
Well,
so
man, you're in the top like 1% of 1% of the population who knows about this stuff.
yeah, so I mean, if I have to take what it means to be a military robot, right? What task are you performing? You're navigating the terrain. You have to walk, like maybe with cargo, carry things from one place to another. Um, all of those are already sort of possible. Like a lot of humanoid robots are already robust at walking. I think maybe one thing that is in the way of full on deployment is how expensive robots are to make. And the other thing is that maybe they don't have a lot of uptime, right? So maybe some of the best robots can only be up for 3 to 4 hours at a time, and maybe
Wow.
that's not useful for a lot of applications. There's always going to be some kind of potential for misuse as with any technology. So from I think a perspective of a scientist and maybe a roboticist who doesn't work in the military space, what I can say is that we are chasing, I think, really cool applications, and it's still what drives us. Myself, I can only speak for myself, but what drives me is just being able to see, um, technology work to improve the quality of lives for everyone, right? And then coming from being an African as well, I can think about, okay, there's a host of challenges on the African continent. Some of them can be solved with AI, some of them be solved with robotics, some of them just need off the shelf mathematical optimization, some kind of like simplex methods and scheduling problems, this kind of stuff, right? But
Hmm.
I think some of my friends and co-founders will agree with me here is that we um, decided to sort of pursue higher education to upskill ourselves so that we can best contribute to society, right? And yeah, so anything that aligns with those values that maybe I'll be able to do. But yeah, like I think war is a very interesting um application, which is sadly quite grim. And as we get good at the current systems, that people can just take that and just apply it, and that kind of doesn't sit right with me. But yeah, it is what it is. Yeah.
Yeah, it's hard to really see a way around it when you're working
Mhm.
on dual use technology. I think it's not as though we can just stop all scientific development because it could be dual use. That seems like the wrong way to go.
Yeah.
Um, but it also seems like really hard to know if you could do anything to prevent those kind of systems being developed and only get the good stuff.
Yeah. Like I was saying, maybe I don't have the right PhD for this, but maybe someone doing a PhD in diplomacy knows how to
Yeah,
how to
yeah.
avoid the worst of the worst, right? For where we are in robotics, we can be a little bit thankful that we haven't quite achieved full autonomy yet. So there's no robot takeover anytime soon. Robots are still very expensive to actually produce. I think there's also not a lot of kind of commercially viable robotics companies. I'll say, like, people are still, in my view, maybe still at the whole prototyping phase and pilot phase,
Mhm,
and um and only recently have we been able to access or realize how useful robots can be, right? But you can expect that as compute becomes cheap, um and then we can sort of do inference very fast. We can use more complicated models that maybe can generalize very well to unseen scenarios.
well, we really need to see. The
Yeah,
future is coming
yeah.
whether we like it or not.
Yes, yes, but there's also a bright future that we can expect, right? So I'm particularly excited about robot surgeons, right? So being able
Mm.
to, right? So for example, right now, there's not a lot of neurosurgeons on the African continent, right? I'm not saying that we should look at robots and be like, we should buy more robots and deploy them in all the hospitals. But, um, you could sort of decentralize the whole concept of a hospital. Like, you have like some kind
Mm.
of truck with some sort of small localized Da Vinci system like robot that can go to remote areas around the world, right? That are not as well connected. And then, you link them up to the internet. There's things like Starlink nowadays. And yeah, it can autonomously perform whatever procedure that needs to be performed right there without people needing to actually go to the hospital, this kind of stuff. So AI has the potential to maybe make those realities possible, right?
Yeah.
Maybe we have fully autonomous farms as well, and we solve food security, right? There's a lot of other issues that we can solve on the way there. It's just sad that on the other side of the coin, we gain the ability to also hurt each other really bad. Yeah.
Yeah. Yeah. I think healthcare is one of the things I'm most excited about, though. I think like robot surgeons maybe make me
Mhm.
feel extremely nervous. So I want
Yeah.
to make sure they had a good track record first. I don't want to be the first going under the knife to a robot surgeon. But well, I mean, it's
Mhm.
already happening, right? You already have robot surgeons.
Yeah. Yeah.
But yeah,
Yeah, that's an interesting
there's a
issue,
trust
right?
problem
So
there.
100%. So trust is another thing, right? So do you trust like a robotic system to, I don't know, take out your appendix, for example?
Yeah, yeah.
Maybe not. I don't know, right? Right now, maybe I don't. Even if I know how it works, I'm like, yeah, but yeah, like, let me see the code. Let me see the code. So yeah.
Yeah, if you've done your PhD in safe robotics and you're not sure you trust it, then I think I'll wait. Yeah.
You see what I mean? Yeah. So it's there's a lot of, I think, a lot of work to be done, like in getting these systems reliable and safe. And maybe trust is something for the next generation, right? So if you grow
Mm,
up with a piece of technology and you kind of understand it very well, then when you grow up, it's not surprising to have it around, right? For us, I think, this is new, and maybe it's too late for us to, speaking for myself, maybe it's too late for me to trust it. I don't know. Yeah, I've already, have my own perception based on scientific movies of like what robots should be like, and also having seen my own code and seeing what I've made robots do, and broken a few fingers every now and then of the robotic system. I'm like, I'll maybe also wait on getting signing up for robot surgery. Yeah.
fun.
Mhm.
Well, I've really enjoyed chatting to you, Kwanda. It's been great catching up and hearing about your research, and thanks for coming on. Really enjoyed it.
Yeah, thank you very much for having me. It was a very fun chat, and yeah, I hope you have a very lovely 2026. Yeah.
Thank you. You too.